Hello everyone, welcome back to the post-break session. So now I would like to continue this session, but before beginning with that, I would now like to introduce to another distinguished academician, Professor P.K. Gokuldas, who is currently designated as a professor at Tallinn University, Estonia. Professor Prashant has considerable expertise in extensive cross-disciplinary research activities in manufacturing of different types of materials. Professor Gokuldas has extensively contributed to several research grants supported by both national and European levels. He has nearly 200 peer-reviewed articles in international journals with H index of 44 and around 8,750 citations. Sir, I would like to request you to come on stage for the keynote address. Please, sir.
So good afternoon to everyone. First of all, I would like to thank the organizers for giving me an opportunity to present something on additive manufacturing. So previously I was not sure how the audience will be, so I have made a presentation which will be very basic, covering the different aspects of, or covering the different processes that are being used nowadays in the field of additive manufacturing. And then I will try to give some glimpses of metal additive manufacturing and the processes that are associated with metal additive manufacturing. So probably it may not be visible, the text here. Hello? So this is hello, yeah. Additive manufacturing is one of the processes that fits with the theme of the conference, where we talk about manufacturing for sustainability or sustainable manufacturing, because as you see from the images here, where we use both conventional manufacturing to make a component like a sphere and an additive manufacturing to make the same particular component. You can see we are removing most of the unwanted material from a bulk of the material to make a sphere using the conventional approach. On the other hand, using additive approach, we are adding material layer by layer so that we will use the amount of material what we need to produce such component, where you will have minimal or nil wastage. So it is one of the sustainable manufacturing processes that can produce three-dimensional components with minimum material usage. However, when you want to produce such component using some of the metal additive manufacturing processes, you may need to have excess material which can be recycled every time because you need to have certain specific dead weight all the time. But the material usage is limited or restricted to that particular component which is going to be produced. And it has a very big advantage because since we are producing these components layer by layer, we have the flexibility in terms of geometry. You do not have to worry about the shape of the material because we can, in principle, produce any shape without restriction. And you also have a flexibility with geography because you are not tied with any industrial, or you're not tied with any industry, or you're not tied with any setup anywhere present or any particular location, because you can design the part anywhere in the world and you can feed the data anywhere else in the world. So you have the flexibility both in terms of geography as well as geometry. This is very significant because even in the war field or even in a medical emergency, you can always feed the data and you can produce any prosthesis or you can produce any component at that particular instance where it is required and when it is required. So the process is relatively quick with respect to most of the polymer-based additive manufacturing processes. And with respect to metal additive manufacturing, it may take some time because you have other constraints which consumes time. So in general, the process is rather quick with respect to the design approach, and it can be produced anywhere without any restrictions. So I will try to slowly move through or go through when we can use these additive manufacturing technologies, and then we will see what are the technologies available at the moment. So whenever you want to produce any complex shapes and whenever you want to have any additional functionalities. For instance, this is one of the milling device from Sandvik where they want to improve the life of the milling tool. So they want to introduce some kind of cooling channels where the coolant can exactly come in contact with the tip of the milling tool during the milling operation. So they introduce conformal cooling channels inside the tool itself. So if you want to have such kind of arrangement inside the tool, you don't have any other technologies which can produce such conformal cooling channels other than using additive manufacturing technologies. And again, you can see here, they have a very complex shape. And even within this complexity, they want to reduce the dead weight of the component. And then instead of making a bulk of the component, they have introduced some kind of structures inside so that you can reduce the weight of the component by 1/3 or even more. In such conditions where you want to improve the functionality, where you want to improve the life of the component by reducing dead weight, additive manufacturing will be one of the foremost manufacturing processes for manufacturing these devices. Also here, the main focus is to reduce the dead weight and to improve or increase the complexity. Assume if you want to produce such a shape using a conventional manufacturing process, you have to mill so many areas and it is going to take considerable time. But on the other hand, with additive, we can produce this with ease and without much time to expose. Similar, this is a typical example. This is one of the burner heads which has been used by Siemens for quite a long time. And this one particular component is assembled from 18 components. So in order to save the assembly costs, Siemens has come up with the use of additive manufacturing technology where the same component can be built in one piece instead of assembling 18 particular components. And for producing this particular component, Siemens has developed an additive manufacturing park in Sweden where they are producing this particular component for the whole year using 10 different machines. So even bulk manufacturing is possible through additive route. and you can save the assembly costs by introducing additive manufacturing, because this will be the only process where you can save such assembly costs for such complex shaped or sized components. Again, when you are thinking of reducing the lead time, additive manufacturing will come to the rescue, because in the same manufacturing, the same build job, you can produce n number of components of different shapes and sizes. We have no restriction with the shape, we have no restriction with the size of the component that can be produced within the same build job. So when you want to have multiple components to be produced with the same material but of different sizes and shapes, of course you can go with additive manufacturing, so that you can save considerable time as well. Again, if you want to save the inventory costs, and if you are going to have different sets of shapes and sizes for different parts, and if you are going to change this design for every component, additive manufacturing will be of boon, because we are not going to make any dies, or we are not going to make any, or we don't have an inventory cost. We are just changing the design through CAD model, and then we are just introducing that design into production. So the inventory costs can be saved if we are going to have even single part with different designs for several components. And if you are changing the design for each component, yes, additive manufacturing could be the technology that can be used. Again, this is again saving the overall dead weight, thereby saving the materials cost. Yeah, so we have seen there are several ways, or there are several considerations we need to consider if we want to use additive manufacturing in a productive and the real-time application. But we need to know what kind of additive manufacturing processes that will be good or that will be feasible to produce these particular components. So I have given the primitive classification of additive manufacturing processes over here. Initially, when the technology was introduced, they classified these processes under such category depending upon the process which you are going to use, or depending upon the material which you are going to produce, or depending upon the deposition mechanism which you are going to employ, or the type of energy which you are going to use for depositing the material. Since all of these additive manufacturing processes are layer by layer approach, we need some kind of energy to be used at every stage, at every layer. Based on that, they can be classified. The energies that can be used for the consolidation processes can be in ultraviolet radiation. In most of the polymer-based processes, you use ultraviolet radiation. Also infrared radiation, that is also used for most of the polymer-based processes. Ultrasonic consolidation, which is generally used for metals to be consolidated, electron beam welding and laser beam, electron beam melting and laser beam. So you can use either laser beam or electron beam, and nowadays people are also started using plasma for such additive manufacturing technologies, where they have used plasma for wire arc additive manufacturing processes. And when it comes to processes, it's not working. sorry for the interruption. So, depending upon the processes used, they can be classified based on extrusion-based mechanism. This is fused deposition modeling, which is the most widely used polymer-based additive manufacturing approach, or based on the photopolymerization or polymerization with combination with ultraviolet or infrared radiation, or you can go using the sintering of the metal powders or using complete melting of either metal powders or wires. Similarly, depending upon the material, they are classified based on either metals, polymers, composites, or resins, and depending upon that, the processes are classified. The last but not the least is using the deposition mechanism, where we use or most of the additive manufacturing processes use raw material as powder, wire, or sheet. So based on that, you have either powder fed processes, powder bed processes, or wire fed processes, or sheet based lamination process, that is the layer by layer. All these are layer by layer, but to be precise is sheet based processes. So this is the primitive classification where people started or people classified the available technologies initially. Now, as per the ASTM standards, we have confined or we have clubbed several processes together, and now the classification is completely based on these 6 different approaches. Either it's going to be sintering, melting, binding, lamination, extrusion, or polymerization. All the additive manufacturing processes, they come under this 6 different approach. For instance, there is a process called selective laser sintering, which is used for sintering either polymeric or metallic powders, which uses powder bed approach and which uses polymers as the starting material. When it comes to laser melting, we have several processes which falls under this category. It can be selective laser melting, electron beam melting, direct energy deposition, wire arc additive manufacturing. There are several processes that involves melting as a primary joining mechanism. And we also have binding based processes where you use external binders or you use resins where you combine them with the powders and then you try to debind the resin or you debind it later so that you get a 3-dimensional component. Or you go for the least used process like lamination process where you use sheets and they are connected together or joined together using ultrasonic vibrations, or the widely used polymer based process that is extrusion based, that is fused deposition modeling, which you can see in most of the labs, and photopolymerization, which is one of the typical examples is stereolithographic process and so on. So this is the basic 6 classifications that are classified to combine all the present additive manufacturing processes in market. So I will try to focus a little bit just on the metal additive manufacturing because that is where most of the interest lies nowadays, and try to give a glimpse of the available metal additive manufacturing processes. The first is called as powder bed fusion process. From the name itself, it's very clear that we are going to use powder as a raw material. We are going to use powder bed for as a deposition mechanism, and we are going to use fusion or melting as a source of joining these powder particles. So there are few processes which involve this particular approach. It's either electron beam melting or laser beam melting. So it is clear from the name itself, either you are using electron as the energy source or laser as the energy source. And then we have also direct energy deposition, which is also using laser as the energy source. So the powder bed fusion process using laser is the most widely used metal additive manufacturing processes, which you can find in most of the places even now in India. And this can produce wide combination of materials. We will see the combination of materials as we go by. And the other one is, as I said, is electron beam melting, where electron is used as an energy source. There are some fundamental differences between electron beam and laser beam melting, but more or less they use same mechanism, same fundamentals, except the energy source is going to be different. And the next is direct energy deposition. This uses either powder or wire as a raw material. You have a laser is used as a energy source. Nowadays, people are also using electron beam. People are also using plasma as an energy source. So basically, the energy source means the raw material, either powder or wire, coaxially, just next to the plate where you are going to deposit your material. So the raw material comes in contact with the energy source, and it gets molten, and it gets deposited next to the substrate or next to the area where it has to be deposited. Of course, this also goes layer by layer, so the deposition goes layer by layer to have a three-dimensional component. The next is the binder jetting. Binder jetting is a little bit different approach than the powder bed fusion process or powder bed fed fusion process, because here we are using an external binder which is fused with the powder particles. So this is again a powder bed approach, where you are adding binders to the powder bed selectively, which is dictated by the CAD data most of the time. And this is a multi-step additive manufacturing process, because all these processes, what we have seen until now, they are single-step additive manufacturing, where you try to produce near net shape component from the powder or the raw material. But in this case, we are going to produce a green compact, and then the green compact has to be then further sintered for extensive time in order to produce a three-dimensional material. So this is a multi-step additive manufacturing process where you initially get green compact, and then the binder has to be debinded, and then you go for a sintering approach. So here you need to have conventional knowledge of sintering, because all the sintering based defects, whatever you have in the normal sintering process, like porosity, distortion, warping, etc., all these things you will also see in this particular process, apart from the biggest advantage of producing components in a three-dimensional manner with no restriction with the shape and size. The next approach is the selective laser melting. This is, we saw that this is known as powder bed fusion process. This is the most widely used additive manufacturing, metal additive manufacturing process. And like most of the metal additive manufacturing process, it also has, we can classify them to have two different steps. The first step, we call it as the computational part. And the second step will be the actual process as such. In the computational part, initially we need to develop a CAD model, or we need to develop a three-dimensional model through any software. And then the additive manufacturing machines, most of them, they need the information layer by layer. So we need to divide the entire information in a layer by layer format, which is known as slicing. And even before slicing, we need to introduce something called as support structures. If you recall in this image, the deposition is taking place over a substrate plate. In order to remove the material easily from the substrate plate, we try to introduce what is so called as a support structures. They are nothing but hollow structures which are normally weak, which uses different process parameters than the bulk of the material. So we have to introduce such support structures, and then that is also has to be sliced. So this sliced data can be fed for a three-dimensional, producing a three-dimensional component. When it comes to the actual process, this is the powder bed fusion process. You have a powder layer which is spread, and then the laser is illuminated, which selectively melts the powder particles. And then the second layer of powder is deposited, and then this iterative process continues until the entire component is built. I skip this. So basically, this is how it works. You have a thin melting by laser, and then you have multiple laser scans within each layer, and you will have multiple layers to produce a three-dimensional component. Only thing is it is advantages you can produce with any shape you want. There are a lot of parameters which affects. I'm not going into the details of these parameters because they are quite extensive, but I just wanted to show that if you're similar to any welding approach, you can also select the process parameters with the combination of laser speed, laser power, and other laser parameters, and see where you have a very good melt pool, and depending on that, you can narrow down the process parameters. If your process parameters are not going to be correct, you may not get the intended shape of the specimen. Either the energy might be too little to build the specimen, or the energy will be too high so that you will have such cracking in the specimen. So you need to optimize in such a way that the melt pool should have sufficient strength and should have sufficient dimensions so that you will be able to produce your samples without any restrictions. The most important thing which I wanted to mention here is that any of the additive manufacturing processes you use, you have anisotropy in terms of microstructure, you have anisotropy in terms of properties. The anisotropy in terms of microstructure will be also along different length scales, because if you see the top view, you have a different microstructure arrangement. If you see the side view, you have a different microstructural arrangement. If you see the front view, you will have a different microstructural arrangement. So depending upon the way in which you test the sample, you are going to have different properties, and this cannot be avoided. Even if you are going for a mechanical property at the nanoscale, depending upon the length scales you are going to have a different properties which cannot be avoided. So the most of the material that has been used for this selective laser melting process is, people started with titanium-based alloys, especially for aerospace applications and also for biomedical applications. Then people looked for aluminum-based alloys, again for aerospace application, iron-based alloys. Nowadays people are working with nickel-based alloys like nitinol, shea memory applications, Inconel for high temperature applications, cobalt-based alloys for dental applications. This is one of the processes which can produce most kind of metallic materials that are available in the market today. But it also comes with a restriction. As I said, the properties are anisotropic. The same material can have a different set of properties depending upon the laser parameters you use or depending upon the processing conditions you are using. So it is very hard to match any property with any material, because this is one material which is showing different kinds of properties depending upon the processing conditions. So we cannot have one numerical figure for property, but we have to give it in the range which varies widely in terms of both strength and ductility is concerned. So this is because you can see it as an advantage, because you can tune the mechanical properties of the material based on the applications, but at the same time, if you are changing any of the processing conditions for defects, you are going to change also your mechanical properties to a larger extent, and you cannot, when you are calculating a factor of safety for any particular application, it's going to be getting difficult. So I would like to summarize here by saying that there are several additive manufacturing technologies that are available in market, but most of the metal additive manufacturing is run through the powder bed, laser-based powder bed fusion process or the selective laser melting process. And there are several challenges that exist both in terms of microstructure and properties, which has to be overcome in the coming decades so that it can be, the products produced by additive manufacturing can be used for wider applications. At the moment, most of the products that are produced using additive manufacturing or selective laser melting is used for static applications, especially because of this condition that you have an anisotropy in the microstructure, and if you are using for a dynamic or a moving or a kinetic applications, the material fails prematurely than it has to. So for static applications that works well, but not for dynamic applications. With this, I would like to summarize, and I would like to thank you all for your patience. Thank you.
was indeed a wonderful presentation. Thank you for sharing your valuable knowledge, sir. Now I would like to introduce you to another eminent academician, Professor R.C. Singh. He is currently designated as a professor in Mechanical Engineering, Department of Delhi Technical University, Delhi. He is involved in activities of Center of Advanced Studies and Research in Automotive Engineering. He has also acted as investigator of Minister of New and Renewable Energy, Government of India sponsored project. He is also an investigator of PCRA sponsored project and of Yanmar Co Limited, Oscar Japan funded project. Sir, I would like to request you to please come on stage for the plenary talk. Have a big round of applause for Professor R.C. Singh. Thank you, sir.
First of all, I would like to thank the organizers, means whatever the university administration is there, they have again, I think I am audible to you. As being a teacher, I can take this stage as a privilege from you people. So thank you very much that you have given me the chance here. And already it is a time that whenever we have a lunch is there and our mouth is watering there, so it is very difficult for us to have a class in such a situation. So, but let us bear with me because I am also of a same category as you people are there. So all the researchers, all the academician, students are there. My lecture is related, means whatever I am saying the lecture, it means only one way is there, and after that we have a question answer is there. Or in between you can also ask me the questions. So let us So let me start. I will not take too much time, but in a small, I will try to explain whatever be that. First of all, means here I would like to convey that my presentation in such a way that what a researcher has to do. Means, thank you, I have not taken the names, I have not taken the Professor Kumar, and so many are there. So just due to this time, I am just rushing to that part because it will take some time. So I told you that my presentation is in the summarization way of what a scientist should do whenever he is going to present a research activity in the sense of the research. Means in the sense of whatever he has done. Means here you will able how we are coming here. On the morning already you have seen that the chief guest already have given the concept of fusion of science and technology. On science and engineering you can say, means theory and technology is there. So it is based on that one only. So here my aim is that to conclude that part with the help of this topic, that is a tribological study of piston ring of stationary IC engine. As being a mechanical engineering or something like that, we are aware of IC engine here. And here the new term you can see, but it is a very old one also, that is a tribology is there. Or tribological means the science related to that one is there. So that one is there. So first of all, I am coming on the definition only. Many of you are aware of that one. Tribology, yeah, tribology, sometimes we are saying as that one. So it is meant from, you can see that TRI is there. So sometimes people are using that. This one is a science of friction, wear, and lubrication. Means three are there. So there is a confusion that it is related to three only. No, it is not at all. Okay, after that, people are thinking that it might be TRY, try, means again and again you are trying. So the science related to that one, whatever we are investigating, that is a part. It is not there. Somebody are saying that it is related to the tribe, TRIBE, means it is a study of the something that is within the, it is related to the very remote area. So it is not also that one, but it is taken from the Greek word that is tribos plus logi is there. Means tribos means we have a two elements are there, means two bodies are there, and we have a relative motion for that one only. So whenever we have a relative motion and the science related to that one, that has been introduced as tribology during this Second World War. So that concept has come into the picture, and so many work has gone, and slowly in all over the world it has been introduced as a tribology. And you will find that everywhere in general universities, the new lab or new scientist or some new faculty are there, they are working on it. So this one is related to the tribology is there. So here, you can see here the characteristics of the film of intervening the materials between the contractive bodies are there. Means I have told you that we have a two bodies are there, and in that one there is a relative motion is there. Means here we have to conclude that we have a two bodies are there, and they have a relative motion is there. So it may be solid contact will be there may be a liquid may be there, or it may be a gaseous stage is there in between. So the between whatever acting is there, that is considered as a lubrication part, or sometimes we are using the three body also. So here, this one slide I have taken from the bachelor's book, and this one is a very important one also to understand what is the application of the tribology is there. It is not always that we are introducing this tribology only to reduce the friction. Sometimes we require more, sometimes we are requiring more friction. Okay, for just we have a walk is there, then some optimum the coefficient of friction must be there. If it is too much, means too high would be there, it means it will take too much time, too much energy. If it is too less, just like this, we have a ground is there is a chance of a slip. So we cannot run here, but we can walk easily. So according to the purpose, according to the whatever the requirement is there, we have to define, we have to construct our surface. So here I mean to say you that this slide is related to the applications part. Suppose we have a shaft is there, it is rotating into the bearing. Certainly there we require the friction should be less. And so here you can see that it contains the two part. One is the friction, another is the wear is there. So it has a more value or less value. So what would be the combination would be there? It may be a 4 combinations. So all the combinations has been written here. At the top, right hand side, you can see that there is a minimum wear and minimum friction is there. So that is a one part. That is the bearing, gear, cam, slide ways are there. There we require such a property. And another one you can see here, the minimum wear and maximum friction is there. So brake, clutches, okay, shoes, clutch, tires, there we require such type of a behavior of our material. Okay, so it is related to that part only. Another one is that you can see here for the minimum friction and maximum wear is there. So in that case, you can see that our pencil and some sliding would be there that would be used. And only one example is that I have found for that one, that is the maximum friction and maximum wear. That is meant for only the eraser. when we are using eraser to take out whatever the blackness is there from the copy. At that time, we are just putting our eraser to have a take out of that blackness. Okay? So whenever we are using that pencil, जब हम pencil use करते हैं, वो कुछ गलत हो जाता है तो उसको हमें erase करना पड़ता है. Then we are using eraser. और erase करने के बाद उस rubber पर, on that rubber, the blackness is coming on that one. So again we have to remove that layer. So what we are doing means whenever we are, suppose we are the child of that nature, or even today, we are putting on our clothes. So whenever we are putting the clothes, that layer is again vanishing out, a new layer is coming for the new application. So that is that application is there. Now the important properties, that is the material is there. Already you are aware of. Material is related to because this is the first conference and it has been written as sustainability is also there. So I request from the organizer that continue it as many as international conference they can do. Okay, so that is there. It is the starting, you can say, is sustainability is there. So it means we have to take care for this material part. Already for the manufacturing, first lecture is given by him, that is the additive manufacturing. Already you are aware for additive manufacturing. Nowadays, due to that one, whole building has been constructed nowadays due to that one. So that part is already taken care by the previous speaker. Now I am coming here for the material only. So all the materials, if we are going through that one, what we are observing, we have to go for its characterization. As he has pointed out that one, that whatever with the SEM is there, FESEM is there, whatever the structure is there, we have to look into that one. So this one is also one of the way that whatever the general surfaces are there, when we are going to analyze, this one is taken from the Prashant Sahu book, that Industrial Tribology by Prashant Sahu. So here you can find that if another material is there and we are cutting that part, whenever we are cutting, so analyzing that one, what is there, different layers are there, and its thickness varies according to the whatever the applications we have used. Means whatever the process, manufacturing process we have used, accordingly the layer is there. It may be a nanometer or micrometer would be there. So here you can see that we have a Belby layer is there, oxide layer is there, deform layer is there, and base material of course is there. Means what I mean to say you, whenever we are going to have any process, in process you can name as we are going for the lathe only. When we are going for the lathe or with any cutting process is there. So we have in contact two materials are there. One is a cutting one and another is on which we are doing our process. So the layer, one material particle is inserted into the another one. That is a Belby layer is there, and its appearance is near about 1 to 10 nanometer is there. Okay, so it is a very less one, we cannot analyze, but again it varies from one metal to other metal. Means whatever the manufacturing process we are using and whatever the materials we are using. So that is the one is there. Another one is that oxide layer. Already we are aware of in kitchen. Kitchen mein kya hota hai? We have utensils. We have a steel is there. We have aluminum based materials are there. So you might be observing at that case that at that point, at certain point, if we are leaving this aluminum, a black layer is there. So that is the oxide layer. Means new materials, they are coming into the picture and a layer is already there, and whenever they are interacting with the oxygen, or you can say air, so that layer is in itself is the oxide layer, and its thickness varies from, you can say 50 to 150 micrometer like that. So after that, deform layer is there. Deform layers, it may be observed only when we are observing through the FESEM or SEM like that one. Means a small layer is there, and we are observing that the layer, their boundary layers, or you can say the boundaries were closer to the surface. So that one is there, and after that we have a parent material structure, we are observing that part. So this one is a very important to understand whatever the materials is there and its properties. Property of the material is varying according to the our processes. So this one I thought that you must be aware of the whatever with the different layers generally we are observing in the material, okay? And already you are observed that when we are going for the forming letter, so suppose the forging is there, so we are putting a pressure on some material, and what we are observing that the deformation or these boundary layers, they are coming towards the surface, and after that its property means hardness, toughness. Toughness is based on the inner surface. Hardness is based on the upper surface only. So the hardness increases only due to that coming closer that boundaries. So that is another part. And here some coefficient of friction has been given. So here whatever we are observing, I put this slide only to make you aware that if we have a new material is there. New material means जब नया material हम manufacture करते हैं, and whenever they are coming closer, they are sticking to each other very well. Means at that time, the coefficient of friction is too high. And we have studied that the coefficient of friction is near about 0.3, 0.2, like that. But in actual sense, if we are going through that one, whatever with the coefficient of friction would be there, so it is going, its value may increase up to the 1,000 only. In some, for that, some experiment has been conducted for that one. Means if we have a one book is there, another book is also there. After that one page, दूसरे का दूसरा page, फिर तीसरे का. So whenever we are putting the different pages along this one, and after that holding that one, if we are trying to make it away, detach that part, we are not able to detach it. So it means that coefficient of a friction between the different pages has gone up to the multifold times. So in that case, you can see that here, so here I want to tell you only that one. If the same material is there or the different materials are there, if it is a new one is there, fabricated one is there, even it is a gold, it is a silver, or something else is there, for the new material is the higher one, and for the old one, that will decrease that part. So here it is a slide is related to whatever be the lubrication part has been done for us. Means if we have a lubrication is there, lubricant is there, so we can assume that one part has been attached with the one surface, another would be there, in between there would be a layer would be there. Another one that is a very important one is there for our analysis. Slowly I am coming into the deep of this subject, okay? So, but after that I will leave that part. This curve is very important to understand how the coefficient of friction is varying with respect to the velocity, okay? So this one you can see that we are saying that is Tribology curve because Tribology has discovered this one. He has done so many experiments, and after that, if you search on the net, you have a more than 1,000 of this type of a curve. Even my own, whatever the experiment I have done, it has given this part, okay? So, Professor Ankit is also here. So whenever he will do that part, he will have time. Certainly he can also have his own curve for his own material. Okay, so you all can have your own curve. So whenever you will search on the net, you will ask for this type of a curve, you will find that there is a thousand means curves are there. So whatever I mean to say you that if you are the student, you can make your own Stryber curve for your own material. But there you have to mention that part that my material is this much and with this velocity, how the velocity and how the lubrication is playing an important role and whatever with the curve nature is there. Nature is a similar one that earlier it is having a boundary layer lubrication is there, means solid contact is there, in between some would be there, then the mixed zone is there. One part I have left that part, that elasto-hydrodynamic lubrication is there, where you can say that this one is a minimum one. Okay, so there would be a minimum one at this point. Let me take this opportunity here. It is a green color. Okay, let me. So here, whatever we are observing that this coefficient of a friction is minimum at this place. Okay, so this range, here we are observing that this, our material, whatever the material having the relative motion, one has some elastic deformation is there. You can have a felt of that. Let me reply in another sense that how we can felt that part. So for that one, just think, we have a banana peel is there. If we are putting our leg, certainly without putting any effort, you will fall down. So that is a type of a thing is there in that elasto-hydrodynamic lubrication. Okay, whenever the deformation is there, it in itself, it tries to make you, it compel you to have a slide on it. Okay, so at that time, the coefficient of a friction, you might be observing here, it is near about 0.001. Okay, so at that time, means here in this figure I have not shown, but it is there, elasto-hydrodynamic lubrication, and hydrodynamic lubrication is already there, and we want that our, whatever we are going to design, that work for the hydrodynamic lubrication, because that one is known as a stable zone. Okay, fine. So that is one of the fundamental is there. So we are defining for that one, and that is used here in the general bearing. Already you are aware of the general bearing as being a mechanical and the material person. So here, if we have a solid contact is there, you can see it is the first phase is there. If we are rotating without having any lubrication, certainly against the relative velocity, the coefficient of friction would be the means frictional force would be that. It will try to climb the shaft. At that time, the coefficient of a friction will be very high and the wear would be also very high. So here what I want to tell you that during that period, our wear would be more. So how to reduce it? Only the thing is that we have to put some lubricant in it. So whenever we are putting the lubricant, its characterization, its characteristics changes. Means whatever here that it is one is there. It is on the left side is there. Now it has come on the right hand side. Okay. So its characterization, its characteristics will change in itself because it has a relative to one, and after the relative to another one is that it means it is supporting to each. Now I am coming the another one, that is a wear part is there. Okay, so already you are aware of that. It is a removal of the small part from the both the solid, and this one is considered as a just, we cannot have a scratch part is there, but it is a small, very tiny removal part is there with reference to the whatever be the original we have a weight is there. For that, you are aware that when we are going to weigh for that one, even the small pressure of this fan, whatever the pressure is there, it is affecting on that type of a nature of balance that is taking care for that pressure also that we are using to find whatever the wear characteristics is there. So it is a progressive damage, you can say, for any element is there. Even it is used for the human also. We are daily, means you are aware of that one, that we have a skin is there. It daily means after 2 or 3 days or 1 month, it is just having a new one is there. Similarly here for the blood cell also, you are aware that it has some life is there and a new cells are coming there. So it is a habitual of that one. It means progressive damage is also whenever it is in the contact or it is not in the contact. And nowadays you are observing that companies are giving that we have a mobile is that its life or its guarantee is for 2 years or 3 years here there. It means they are intensely putting that it's one element or one part will, surely it will be damaged by that time. Okay, so this type of things are coming also in the picture. So these are the different wear mechanisms there. Let me take my case study. I will take 4 or 5 minutes. So this is also a very general one. Wear mechanism is there, and after that, whatever be the means the operating conditions are there, and whatever be the resources are there, for that one is there. So this one is there, and again the strike curve. Already I have told you about that one, and certainly we have whatever with the properties are there which are making it to have happen before we are going for the study. So for that, viscosity of the lubricant is very important for us. So there is a standard ASME methods are there, ASTM methods are there. Accordingly, we are measuring that part. So this is another one is there. Now, I am coming here on the case, my case study. So up to now, whatever I have considered, that is only the general thing that one should know what is going to happen there. So one case study is there. Just bear with me. This would be a very useful for the starter who are starting there, this study purpose or writing this paper. I have seen that whatever the book of abstract is there, for that I thank to Professor Shankar Sahib and his team, the wonderful work they have done, and for that, whatever the editor has done it. So that is also a wonderful thing, and it is not the easy work actually. It takes the time, it takes your energy, so many brains, and many times you have to contact whatever Professor Anand has done or his team has done. I congratulate whatever you have taken here, you have put on our set. That is a wonderful thing you have done. Wonderful activity is there. So this one is there only that we have a one engine is there, stationary engine. Generally we are using for earlier one, and on that one experiment has been conducted here. So this is the hand crank. IC engine is there. Another one is there. How we have to start? We have to think whatever the need is there. So according to the need, we have to focus on that one, because already you are aware that one proverb is there. Means need is according to the need, we have some inventions are carried on that basis only, that provoke us. So this is there. So anyhow we have to, even today, we have to save our fuel, or nowadays electric vehicles are there. Even though you can think that for the 20 years, more up to the 50 years for some places, we have still we can run our IC engine on that one, only on the fossil fuel. That's why I have taken this case, and this one here we have to use a different sense. Means in the morning, one expert has come that at least at the end of this seminar, we have to come with some solutions, some thinking matters. So in that one, this slide will help you to what to do. Means smart design is there, nanomaterials is there, and eco-friendly lubrication is there. So capturing the exhaust emission is there. So the different things, means different parameters are there for which we have to work. So this one is you can say that we have a IC engine is there. It is an open type where means we are working on that one. So here we at this place we have a piston rings are there. You are observing here we have some slots are there. So there we are using the piston ring. So our work was only on the piston ring, how to define the profile of the piston ring, because you are aware that if a fish is there, on the scale you are observing that there is some pattern is there. So that is also playing a very important role for its swimming purpose. Similarly here, for having the relative motion of this piston ring with the liner one is there, so we have to make some profile for it. And as being a design engineer, we are aware that in IC engine, if it is a slow speed engine, in that case, number of the piston ring is more than the high speed engines, okay? So it is going up to the 6, 7 like that are used in ships. And here we have near about, you can say, in bike or scooter, we have a 3 is there or 4 is there, or sometimes it is working on the scrap and whatever with the controlling of this lubricant is there. So this one is the one is there. And now in some literature, means how we have to come over that one. In some literature, I found that this whatever the fuel energy is there, means fuel energy means whatever the mass of the fuel has been used, multiply by its whatever the calorific value is there. So that is its total energy is there. So I think it is more. So I am coming there. Means it is just a distribution of the fuel energy. This is a distribution of friction energy, because my work is here, so I have come here on this friction only. And after that, whatever the action is playing role, this is the one is, you can see the cylinder is there, piston rings are there, in between red color is the lubricant is there. So this was there, and here we have to find whatever with the piston rings are there, and there we have to put the profile. Already you might be aware of this part also, that when we have a process is there, means it has a reciprocating motion is there. So in that case, you might be observing that how many types of dynamic forces are acting at that place. So we have a straight force is there, means whatever the compressive is there, sometimes the tilting is there, and that we are saying as a twisting is there. And apart from that, some action of the burned gases are also playing important role. So in that one, blow by and blow back is there, and its mechanism is here, and we have to introduce that part also. So this one is a piston ring, you can see whatever the thickness and height is there, and our work is here only. So here what I have done it means I am just concluding it here, because I am observing it is too late, and your patience is also up to that one only. The class is useful only for 40 minutes, that I know that. So already I have taken that part. So whatever I have done it here, I am just explaining within 1 or 2 minutes, is that here on the piston ring, I have gone for the profile. Different profiles are there. I have analyzed that one, theoretical, and after that, I tried to make it, because it is very tough for the micro level of cutting on the surface is very difficult for us, so we have gone for that one. So after that, that profile has used in the IC engine, and after that we observed that its efficiency has increased. At the beyond that, the whatever be the exhaust output is there also we found that there is a change in that one. So after that, there is a one company is here, I think you might be aware of, Shriram Piston Ring and Compressors are there. So they came and they saw that part, and after that they used that part also for for the process, means for their R&D department. So here I am leaving that. If you want, I can go much more that one. Yes. So this one is my Reynolds equation, well known. 1886, a mathematician has derived this one, and we are still working on that one, modifying that part. So these are the different parts are there. So here we did the testing, and we have found that the result is very favorable for us. So this is a type of, you can say. So here I am just leaving because it is a boring for you people. So more technical is there later on. Okay. So thank you for your patience, and at this moment, whatever you have given your time with an empty stomach. So again, I thanks to organizers and others for their giving me the opportunity. Thank you very much.
I hope I was audible earlier as well. Yeah, thank you. So I would like to move further, and we have our last academic, eminent academician that I would like to introduce to you. We have Professor V.S. Senthil Kumar. He's currently designated as a professor in the Department of Mechanical Engineering, Anna University, Chennai. He has the experience, 24 years experience in teaching and industry. He has contributed 153 journals and presented 106 papers at several conferences worldwide. He has also been granted Indian patent through IPR, Anna University, Chennai, in the area of manufacturing of fuel cell. Please give him a big round of applause, please. So.
So it's not a right time to give it because already you have hunger, I think. Anyhow, I have to fulfill my role. No, my student, Professor Shankar, have invited me. You have to give your plenary talk on your area, sir. Then I readily accepted. I have to thank your opportunity for given by the university as well as the organizers. Here, the topic is the materials manufacturing and sustainable developments. It's a right topic because the Indian nations are depending on manufacturing industry because 20% of major role they are contributing. Nowadays, the materials and manufacturing both are interdependent. If you have material, then the manufacturing processes can be carried out. So the raw material is converted into finished product by means of various manufacturing methods. There are methods, older methods, casting and welding, forming, as well as the metal cutting and composites. Now, recently our professor has told that is additive manufacturing and all. Apart from that, now latest developments are there in the manufacturing field. One of that is the friction stir processing. So sustainable development is there in the manufacturing area. So friction stir processing also is a contributing major role, because many of the industries nowadays, they are facing many challenges. One of the challenges, wear and tear. Already our Professor Dr. Singh told the wear is a big issue in the industry. How to address that one? Now, suppose any part, small wear is there, then immediately we have changed the structural part. Then instead of that, you can add the strength with the help of some processing, then we can save the cost of the material. So in that point of view, this friction stir processing is one of the useful process. Many of the researchers are doing this area. Here the history of that given from 1885 to from 1930 periodically, and now the friction stir process is arrived at 2000 year 2000 it is developed. Okay, it is arrived from the friction stir welding. So while doing the friction stir welding, then why don't you attempt the friction stir processing? Because the friction is here used is a heat generated, that with help of the heat generation, we can apply that technology into the material and making a material as a plasticization. After that, we can process the material into required shape as well as the region. We have to concentrate on that. For example, we take a case study, the Columbia air vessel, that is the space vessel, they get failed. Why? You know what is the reason on that? Because material failures. So material failure, the joining material is not properly is there. So to address that, what are the challenges are faced by this spacecraft? Then the scientists are attempted some investigation, finally concluded that the welded area is not that much strength having. So because of that only the failure is occurred. So after that, they are introduced this technology. They replaced many frames in that this one. Then the newest tanks, including ET 134, have been welded using a new welding technology called friction stir welding. A technique better than the conventional fusion welding, because the conventional fusion welding, suppose we are doing, the lot of fumes are arised. But this technique, there is no fumes, there is no adding material. Simply they are processing and welding only is carried out, joining the solid space. Welded joints more than efficient, yielding 80% of the base strength. So base material, whatever strength is available, that is added than that particular nugget zones. So friction stir welding was invented in the Welding Institute of United Kingdom in 1991. It is a solid state technique. It was initially applied in aluminum alloys. Later, a lot of materials have been introduced. Now we use titanium alloy and other steels also they can weld using this technique. This is a process involved here. The position of the material, rotable, that is stage by stage, what is the method we are adopting in the welding. The importance of friction stir processing, surface properties such as wear resistance can be determined by service life of the components. These are the mechanical property as well as the material property have improved in this technique. It is a process. You can see there are two pieces which may be positioned with the help of fixer, with applying a force on that, with the help of the rotating tool having a tip, the processed region is carried out, then, and the material is being welded, joining is carried out. So this is the process. There are the advancing side is the right, where the tool rotation direction is the same as the tool travel direction, and friction stir welding is relatively new solid state welding process. The tool serves the three primary functions. One is the heating the workpiece. With the help of the solder, heat is generated in the surfaces, and the movement of the material to produce the joint. because plastification is carried out at that region, the material has been gone through this one area to another area, then and settled down. After that, the solidification is, joining has been carried out. Containment of hot metal beneath the tool solder. As a result of the tool action, when performed properly, the solid state joint is produced. Because the tensile strength is very high in this, particularly in the friction stir welding. Because of various geometrical features, the tool material movement around the pin can be complex. So fully recrystallized equiaxed fine grain microstructure is obtained. Suppose you take the specimen in cut through and using a microstructural testing you have done, then you can find out the grain size is very refined grain size may obtain. So the friction stir processing is adaptation of friction stir welding. The low amount of heat is generated, healing of flaws and casting porosity, and this can be used in generic process to modify the microstructure, change the composition by selective location. Selective location means suppose wear and tear is there in some automobile parts, you concentrate on that, okay, you adopt this technology, you can strengthen the structure. So FSP is one of the solid state processing technique that has been 3 unique capabilities. One is rotating tool, another one is pin is plunged into the workpiece, and fourth one is the shoulder towards the surface. Now the tool traverses on the plate until fully recrystallized fine grain microstructure is obtained. These are the parameters I have taken for this process. Suppose for doing a friction stir processing, you have to consider these parameters. One is tool rotation speed, traverse speed, axial force, and shoulder diameter, and pin diameter, profile, tilt angle, workpiece material, shoulder and pin material. So with the help of these parameters, we can optimize which condition we can do the operation and all, friction stir processing operation. There are many experimental techniques are available, ANOVA, Taguchi, then other multi-response techniques are available, multi-criteria techniques are TOPSIS, RSM, response surface methodology. There are many techniques. We can choose that which techniques optimum for this particular, this one. Lot of research is going on in this area. So the process parameters. So the different microstructural zones existing after FSP. Suppose if you are doing the processing, you take the specimen and cut down this a different region. What are the regions are? One is unaffected material parent metal and heat affected zone and thermomechanically affected zone and weld nugget. So it is pointed out in this pointed out these regions are here. This number 1 is the nugget zone, and the extreme it's a parent zone. Okay, not metal heat and not affected in the zone is 4th zone. And what happens inside the process? Here the plunge, the phase where the process is initiated. The second one, the main phase where the process is made, and termination phase where the tool is withdrawn from the workpiece. These the phases are inside. So what happens inside, you can see in this diagram clearly, welding direction, then the tool rotation, as well as preheated zone and initial deformation zone, extrusion zone, and forging zone and cool down zone. There are different zones are available. We can see each zone, what is the material property and what are the microstructure available in these regions. We can do the research. So tools for FSP, it's another important challenges during the friction stir processing. So the tools, what are the tools can be useful for this process? We have to study the research. Based on the research findings, we can select the tools. One is advancement in tools lead high production speeds, higher workpiece thickness, and improved property. Okay, then has enabled the processing of high melting point materials such as titanium, steel, as well as copper. New tool features have been developed for the goal of reducing process forces, increasing the robustness of the process, and simplifying the welding control. So the different features are used for different practitioners, FSP depending on the materials being processed and the process performed goals are required. Because the researchers nowadays initially they have started aluminum alloys. After some periods, this will be adapted to all materials. Even and the titanium also we are doing. And also metal matrix composites have been developed using this technology. These are the tools have been used for our studies. The tool profiles, that is how they are doing. If suppose threaded profile, how they are creating the strength, increasing the friction stir processing method, and other profiles also we will see one by one. There are different profiles are available. Each profile creating the different strength of the materials. So the advantages of this particular technique, no harmful emissions are created and no shielding gas is required. Here no minimum surface cleaning is required, eliminate grinding waste and eliminate solvents required for decreasing consumable material savings such as wire and any other gases. Metallurgical benefits, solid phase process, low distribution of workpiece, good dimensional stability, no loss of alloying elements, and excellent metallurgical properties, and fine microstructure, absence of cracking, and replace the multiple parts of joint fasteners. This is the metallurgical benefits may be obtained using this technique. Any process, there is advantage as well as limitation is available. Now we are going to see the limitations also. Next advantage, energy benefits. This is environmental free, there is no fumes are there, green manufacturing method, and only 2.5% of energy needed for laser weld, decreased fuel consumption in lightweight aircraft, automotive and ship applications. It's a green technology due to energy efficiency, environmental friendliness and versatility. And limitations. There is a initial and exit, there is a holes are developed in that case. That part we have to discard it. That is the wasted in the material. This is one of the limitation is available in this technology. Large down forces are required, heavy duty clamping necessary for hold the plates together. That means proper clamping is you have to provided in this process. Insufficient clamping, it will tilt during processing. So less flexible than the manual and arc process because there is a constraint is available. We have to specify the fixer size as well as under standard place you have to use. And another one is often slower transfer rate. That is efficiency will be, weld efficiency may be high, but the process rate will be very slow. And a backing bar is sometimes required because because of the heat, sometimes the specimen will stick on the fixed plate. These are the defects or limitation is there in the process. So we can see the limitations. Application point of view, there is many structural applications are available. You can see one by one. Engineers at NASA Marshall Space Flight Center have worked to perfect FSW technique, which will be used to help in the astronauts to moon and further in space travel. These are, we can see here, these are the applications. So the structural parts welded by this technique. Shipbuilding and marine industries, we are used in this technology. And formed aluminum. The heavy structure machine, that is the largest friction stir welding machine, is available in the world, in the NASA. These are the application machines. This machine have been indigenously developed in our university. We have applied a proposal to the DST. They have given the fund. So with the help of that, we have manufactured this machine with the help of the external agency. And many of the researchers are using our Sankar also used this machine. He did research in this machine only. Roughly it's 22 lakhs this machine cost. So with that I stop this presentation because already you have a hunger, you know. I stop this one. I thank you one and all. Any query you can ask. Yeah. Material selection part. Yeah.
We are going in that field.
Yeah, you have to
And sir, second thing,
collect the literature survey. Based
yes.
on the literature survey, which material you can opt for this one. Okay, for
Okay, sir.
research.
Actually, I have just going for the high strength material like steel and copper or magnesium alloy. But when I'm going through modeling part, they just divided in 3 zones: intermetallic zone, and for dissimilar welding, dissimilar material type of welding. So I'm writing code deflux subroutines through
Yeah,
Abacus.
actually, there are already developed models are available.
Yes.
For example, in
I'm
finite
just a-
element analysis, packages are there, Abacus and all. They are constitute a model that is Johnson algorithm is there.
Yes, sir.
Modified Johnson algorithm also is there. They are using for plasticity model. Here, you have to find the K value. You know,
Yes, yes,
thermal
sir.
conductivity
Yes.
value is K, you have to identify. That you can refer the library for the what material you are using. Accordingly, what K value you have to select. If perfectly you have select the K value, you apply in the constitutive model, definitely you will get
Sir,
the result.
but there is less paper available regarding coding part. Coding part is missing.
Why you are coding, you are
Sir,
wasted your time.
I
Already models are there.
No, sir.
You don't develop
no,
any model, don't develop any code and all. Then use the material property and apply on the already existing model, then you can get the result.
Sir, but when we just builded a dissimilar part,
Yeah.
we need to implement some
For
three
dissimilar
zones.
part, maybe either the grade only you are changing. Suppose 7,000
Yes,
series
sir.
or 6,000 series. Like that only, no?
Yes, yes, sir.
Then it is a common no, K value maybe you found theoretically. And you can after that you can use that K value in your model.
Sir, but mostly I have just gone through SK Bag. He's teacher in IIT Guwahati.
Yeah.
And they have just doing their research in Abacus subroutine using the deflux code, subroutine parts, and they have implemented subcoding.
Your main research is you have to weld the dissimilar materials
Yes, yes,
using friction stir welding
Yes,
process.
yes,
That is your objective.
Yes, sir.
So why you
But-
are wasted time on developing a code and all?
Sir,
Already his model is there. You identify the material and weld that one. You find the theoretically calculate the K value. Whatever K value is there, then you apply and get the result.
Yes.
You can compare the strength both theoretically as well as mathematically. Then you can experimentally, then error percentage maybe you can give the report. That is the
sir, I
research,
think,
no?
but it become easier when we just implement. They have implemented code, but I want to write that code.
What is
to-
the usefulness of the code?
so that we can validate our experimental and modeling part.
Yeah,
Yes.
validating
main
the
agenda is
experimental
that.
part. Already developed model is there, proven technology is there.
Okay, sir.
Why don't you use that one?
Okay, sir. Thank you, sir.
Okay, use that existing model and find the K value. That is important. That is K value is the important for applying this model, because this will be derived the temperature distribution. Temperature distribution is one of the critical part in these regions.
Yes, sir.
So that you have to find, and a suitable temperature you can apply in the constituent model and find the values.
Okay, sir.
Okay.
Thank you, sir.
Simple, very simple. Theoretically calculate, use that one and get that one. Any other doubt? Because a lot of research is going on in this particular field, friction stir processing and friction stir welding. Especially in metal matrix composites, one of the route is friction stir processing. You identify the wear out region and make slots and add the metal powder in that region, do the material processing with the help of friction stir processing. You can get a sound metal matrix composites in that particular region. Okay? So any other? Okay, thank you, one and all.
Thank you so much, sir. Thank you so much for sharing your knowledge. Now I have a brief announcement to make for all the presenters here. So earlier the schedule has been shared with you for your presentations. Now there are some changes in that. So earlier you had been allotted room number 104. Now it has been shifted to lab 6. So all the presentations will be going on at 5th floor only in engineering block. Earlier, those who have been allotted room number 103 now have been shifted to lab 4. 102 have been shifted to lab number 1. 101 lab have been shifted to lab number 7. I would like to repeat it. Please just note down. 104 has been shifted to lab number 6, 5th floor. Room number 103 now has changed to lab number 4, again 5th floor. Room number 102 has now shifted to lab 1, and room number 1 has now switched to lab 7. So all will be at 5th floor. I hope it's clear. Thank you so much. Thank you so much for your patience. Thank you for being here. Enjoy your day. And all the very best for all the presenters. All the very best to you. Thank you. Again, I would like to request all the dignitaries and the guests to proceed for the lunch at same place, mini conference hall. Yeah, in mini conference hall. Thank you.